Alright, here goes. Hypothesis testing, and this time we're going to talk about it for population proportions. Let's see what we can do for the last one of the year. Alright, ready to go? So we want hypothesis testings and we're talking about population proportions. This is a short one, so stay awake. Alright, example number 1. Now remember, this is population proportions, so we're talking about proportions, not means. We've been talking about means a lot this semester. So we're talking about a political candidate, and let me grab this pen here. Almost forgot about that. So we want to find out what's going on with the voters. Do we have a good chance of winning? Well, the poll finds that 204 people out of 400 support the candidate. Well, that's over half, but is it that much over half? Should we be spending a lot of money on this political contest? Let's see what we think here. Should we be confident of winning? How confident can you feel with 204 people out of 400? Let's find out. Okay, here's our first mistake is what we've got. Should be P hat. So on slide number 3, I need to make a change. Alright, so we're at 51% basically. We get our null and alternate hypotheses. Since 50% is sort of the default if we don't know anything at all, so we're going to guess that the proportion is 50%, and the alternate would be greater than 50%. In other words, we think we're in line to win the game. So how do we find if there's enough evidence to reject the null hypothesis? Remember, the null hypothesis is it's a 50-50 game, or are we likely to win? Use 4 steps, and if you could be looking at that book, it'll be on page 376. We aren't right now. Step 1, what are the hypotheses? Here's our null, has equals in it. We're in good shape there, and we're interested in greater than or equal. Notice this is a right-tailed test we're going to be performing, so we're going to be looking for a p-value out here if we're using p-values. Collect the sample data. Actually, one thing we should do before we do that, we should decide on the level of significance. Otherwise, we might tend to cheat on this one. So there's our p hat. Step 3. What is the chance that sample result is over 50%? Is it by chance, or is it likely that the null hypothesis is true? So here's our null hypothesis, our standard distribution of the sample proportions. Remember, we also have to remember we need n times p, this is our sample size, times the default proportion of 0.5, greater than 5, and nq needs to be greater than or equal to 5 as well. Q, of course, is 1 minus p. Checking those out first, those are some of the things you should check out. Given those, here's our standard deviation for this distribution of proportions. If it's close to the peak, we won't reject the null hypothesis. It's basically 50-50. However, if it's far enough away, we'll reject the null hypothesis. Here's a picture of what we're talking about. You can pause and read if you like. Here's our z-score that we create. It's a good generic way of looking at things, because this way everyone, regardless of what you're doing, can use this z value. Our population proportion, we put what we got from the sample, and I think this is a little bit of a typo. I think slide 7 should be fixed too. 3 and 7. Need to get back to that. So, our sample proportion is inverse normal, with 0.4. Decide whether we're going to reject the null hypothesis. This was the standard score. It's not over 1.645. Normal CDF. Here's our p-value, which isn't anywhere close to 0.05, let alone 0.01. So there's a 34% chance of our result being there at 51% or even greater than that. Well, that isn't unlikely, so we'll reject the null using the p-value. So we cannot assume that she has a support of more than 50%. It's still up in the air, folks. So the null hypothesis is that the proportion is the claimed value 50-50. Here's our z-score. Here's our population, or sample proportion rather, the 0.51, remember? And this is the 0.5 that we're comparing it against. Put these p's in the bottom at the proper places. By the way, this is that q I was talking about earlier. It's just an alternate way of writing the denominator. You could write the denominator alone. PQ divided by n is another way of writing it. Next, we use that standard score, the same two ways we used it when we were working with the means. Check with the statistical significance by comparing the standard score to the critical values. And we can get the p-value with a normal CDF on the calculator. Decide in advance how significant you want to go for. Otherwise, what if it turns out that the p-value is in between those two? Well, someone might cheat and say, well, I didn't really mean 0.01, I really meant 0.05. That's not right. If it's not statistically significant, less whatever p-value or level of significance we chose, and we won't reject the null. So we picked 750 people, and 92 of those are left-handed. So, 4-step process again. We've got our null hypothesis is that 10% is left-handed, and our alternate hypothesis down here, where am I? Down here, okay. Alternate hypothesis, it's not 10%. So therefore it's a two-tailed test. So here's our p-hat, or proportion estimate, 0.123, that's above 10%, but it is a two-tailed test, remember. So the standardized score is 2.09. Remember, that would look something like this. Is it far enough from the accepted mean to say that this value is exceptional or significant. For a two-tailed test, the standard scores are less than negative 1.96. We know it's not that for this one. 1.96 on the right-hand side. It's over 1.96, the 2.09 we got for Z test score. So it's significant at the 0.05 level. If you actually checked on this, if you were curious about the 0.01 level, it wouldn't be significant. So it depends on the level of significance you start with, perhaps. That's why you need to choose the level of significance before you start your sampling. So the 2.09 gives you, this is a p-value, so at the 0.05 level of significance, you reject null. At the 0.01 level of significance, you do not reject the null. Remember, we take this number, we double it because it's a two-tailed test. In this case, it happens the same way. At the 0.05 level, we reject the null. At the 0.01, do not reject the null. And that's how it goes, folks. That's what it looks like picture-wise. These are the critical points. These are the critical regions, the rejection regions. So the test is significant at the 0.05 level. We reject the null, and we say the proportion is not 10%. And that, folks, is it. You might take a moment or two or three and look at what would be the case for the type 1 or the type 2 error. Now, it's not going to be critical, most likely, whether we made a mistake on just whether 10% are left-handed or not, but if there could be a possibility that would be so important, we would want to avoid the type 1 error. It all depends on the situation that you're working with. Well, that's it, folks. I'll see you in class.